Welcome Algebra 1 students to our review of scientific notation as well as some instruction on how to perform operations with or in scientific notation or with numbers that are in scientific notation. So remember the purpose of scientific notation. First of all, what is it? Then we'll talk about the purpose. We're using it to write, well, this really is the purpose, for writing very large or very small numbers. That should be numbers. Using the product of a decimal and a power of 10. Scientific notation should look like so. We use it in scientific calculations. Should have a coefficient times a power of 10. The decimal number is going to be between 1 and 9.99. You have your multiplication symbol. Usually they use an x, even though we've been told not to do that in Algebra 1. And then a power of 10, so it's going to be a 10 with an exponent that's either negative or positive. Why do we use it? Because some numbers are just way too large and some are way too small to express with standard notation. That's the regular way you write numbers in math. For example, if you look at the mass of an electron here, here's proton, here's neutron, here's electron, 9.109 times 10 to the negative 31 kilograms. If I was to write that out, I would be writing 1, 2, 3, 4, I would be writing 30 zeros total until I even got to a digit that wasn't a zero. That's really long, and that doesn't even show up on a regular scientific calculator screen. You can't even demonstrate that on a regular scientific calculator screen. So that's why we use scientific notation. All right, so instead of me voicing the directions here, I'm going to pause it and write all these out, and I want you to do the same thing. This is review, and you probably can get through these pretty quickly. So start with writing each of these numbers in scientific notation. I'm going to pause it, and here come your answers. And here you go. So start with the first one. 2,000 is 2 times 1,000, or 2 times 10 to the third. Move your decimal point from the end of the number, which is where the decimal point is in a whole number, until you have one digit left to its left, or one digit remaining to its left, and that's the coefficient times 10, the number of places you move that decimal point, that's your exponent. So you see 3, 4, 5, 6.8 times 10 to the fifth, 3, 6, 7, 5.94 times 10 to the seventh, and 6.2 times 10 to the first. Now, we wouldn't see this number used in scientific notation very often, but you can still write it that way, and it might be necessary to write an answer in scientific notation, like that. All right, now for some of the numbers that are much smaller than 1, so I'm going to do the same thing. I'm going to pause it and write it out, and you go ahead and do the same, and then check your answers. So here they come. Quick, pause it, do your math. And there you go, guys. So this time, all of these numbers are smaller than 1. So when I move my decimal point, I'm moving it to the right until there's one digit to the left of it that isn't a 0. So in this case, I had to move it 4 places. Notice that it's a negative 4 exponent at that stage. So that's 3.0 times 10 to the negative 4. Here we had to move it 6 times, so 2.24 times 10 to the negative 6. Here we moved it 2 places, so 8.11 times 10 to the negative 2. And here, 9 places, 1.15 times 10 to the negative 9th power. Now we're going to go the other direction. I give you standard, I give you scientific, you give me standard. So have at it, pause it, and here comes the answers, or here come the answers. Okay, so for these, we were given scientific and going to standard. Again, they're all positive exponents, so all of these numbers are values bigger than 1. And what I did is I moved the decimal point to the right the same number of times that the exponent tells me in order to make this number a standard notation number. So on the first one, it was just 3, so all I did here was add 5 zeros, put a comma in to make the number more readable, 300,000. On the next one, we had 1.7. So the 7 is 1 decimal place, and then 7 more decimal places for a total of 8. Notice it is not 8 zeros, it is 8 decimal places. And put some commas in that one for an answer of 170 million. Next one, we moved the decimal point 3 spaces. So we needed 1 extra 0, 8,920. And on this last one, I moved it 2 decimal places, 951.2. So you might still have a decimal in your answer, even though it was in scientific notation to begin with. So we don't necessarily only use it for gigantic numbers. Sometimes we just use it because that's what we're told to do. Okay, here's the last set of these. Go ahead and put these into standard form. These numbers are all, if you notice, negative exponents. These are all smaller than 1. Go ahead and pause it because here come your answers. and the last set. So this time, remember here, negative exponents, these are all smaller than 1. So I'm moving my decimal point to the left. And I don't want you to think negative exponent, move it to the left, positive exponent, move it to the right. That's dangerous because if you mix it up, or if you get confused about going from standard to scientific or scientific to standard, you can't go with the direction theory. So you want to be thinking instead, negative exponents give me teeny tiny numbers. So you had to move that decimal point to the left to make these numbers smaller. For this first one, move that decimal point 5 spaces to the left. So we have 800 thousandths, I believe. Let's see, tenths, hundredths, thousandths, 10 thousandths, 100 thousandths. Here we have tenths, hundredths, thousandths, 10 thousandths, 100 thousandths, millionths, 10 millionths, 100 millionths, billionths, 97 billionths, 312 hundred thousandths for the next one, and 221 thousandths here. Now notice again, that exponent did not give us the number of zeros. It gave us the number of decimal places. Okay, on to operations with scientific notation. And for this section, I'm going to handwrite in the problem. So let me pause it real quick and handwrite in these problems real quick. Okay, so let's talk about how we're going to multiply this. Well, I want you to remember that you can think of this as a coefficient, and you can kind of think of your power of 10 as your variable. So in this problem, you're going to start off by multiplying the coefficients together, just like you would if you had like 6x squared times 5x cubed. You've multiplied the 5 times the 6. So the initial part of my answer is going to be 35. Let's switch colors so I'm not using the same color as the original problems. 35, and we know that's not correct scientific notation, but we're going to come back to that. When you multiply the powers of 10, keep the base and add the exponents just like you did when it was just regular old multiplying powers of 10. Or multiplying powers with the same base. So x to the second times x to the third, x to the 2 plus 3, 5. Now, here's the problem though. This is not scientific notation anymore. So I have to make this number smaller by 1 power of 10. If I make this number smaller by 1 power of 10, I make this one bigger by 1 power of 10. And the final answer is 3.5 times 10 to the 8th power. For the next one, multiply the coefficient times that multiplier out front. We're not distributing the 5. We are not distributing the 5 because we don't distribute over multiplication. So I end up with 30 times 10 to the negative 8. But again, I've got to make that coefficient smaller by 1, which means I have to make that exponent bigger by 1. Smaller by 1 power of 10, bigger by 1 power of 10, because they balance out. Having trouble finding appropriate music today. Oh, that's better. 3.0 times 10 to the negative 8 plus 1 is negative 7. And this last one, 0.3 times 0.4 is going to be 0.12 times 10 to the 4 plus negative 11 is negative 7. Now this time my scientific notation is wrong because it's too small by a power of 10. So I'm going to make it bigger by a power of 10, which means I have to do the opposite over here. So remember what we're talking about here. We say when we make it bigger by a power of 10, that's because it's as if I'm multiplying here by 10, which means I got to take off 1 power of 10 by making this smaller by 1. That gives me 1.2 times 10 to the negative 8. But never fear, your TI calculator is going to help you quite a bit with this, and we'll see it in warm-up next time. Let's do a couple of division problems. And after these division problems, this video is done. So let me go ahead and jot a couple down for you. Hold on. Okay, folks, we're keeping it pretty simple here, not making them too exotic. I want you to think about the same kind of thing we did with the previous problems where we multiplied coefficients and then multiplied powers of 10. We're going to divide coefficients and then divide the powers of 10 by subtracting the exponents just like we did when these were algebraic problems. So start with 2.4 divided by 1.2. Well, that's the same thing as 24 divided by 12. It's just that they've both been multiplied or divided by 10 to give you 2.4 over 12. Well, the ratio is still the same. That's 2. And then times 10 to the 3 minus negative 8 is positive 11. So you should have 2 times 10 to the 11th for that one. 36 times 10 to the 5th over 6 times 10 to the negative 1. Well, 36 divided by 6 is going to be 0.6 times 10 to the 5 minus negative 1 is 6. But I'm going to have to make this bigger, make this smaller. So this is 6 times 10 to the 5th power. And the last one, again, we don't have a power of 10, just divide the coefficients divide the coefficients, and keep the power of 10, because if there's nothing to subtract, 11 minus 0 is still 0. So 1.5 divided by 3 is 0.5 times 10 to the 11th, and again, bigger by 1, smaller by 1, 5 times 10 to the 10th. So calculations with scientific notation are not challenging on paper. They're even easier when you have that happy TI-84 plus calculator. 834. Let's try that again, Miss LeConte. There we go. All right, so we will look at using the calculator for operations with scientific notation next time. Hopefully this is a nice, quick, and easy video for you. See you guys in class.